We are looking at the Pounded Yam challenge as an example of how we can improvise a new design from existing designs. Consider the yam pounder in the Nigerian market. This particular one has Proudly Nigerian written on it. It does the job, only that it is heavy, expensive, and exceedingly noisy. It worked, and under light usage for about a year, it developed a fault. You got no service, no good address, no contact. You are on your own. In desperation, you might open it up. If you did so, this is what you are going to find. You'll find that what they are calling a yam pounder is actually a packaged grinding machine. They package this grinding machine, a standard grinding machine you can get in the market, put a gear on it, and allow it to drive a rotor, and that is the rotor that grinds your yam and makes a pounded yam for you. Now, this is the full grinding machine that is inside. They have removed, you can see here, they have removed the label so that you don't know which particular grinding machine or who made it. But there is not much change in the grinding machine. Or once you turn it on, you are turning on that grinding machine, and all it does, it just makes this one move. And you can see what happened to my own is that the gear teeth wore out as a result of poor gearing and expensive rotor, very heavy rotor for the job. Now, here is the rotor itself. This is the rotor in the pounding machine that was actually sold as a manufactured product in the Nigerian market. If you look at this rotor, you will see that it is a welder's idea of a rotor. All that there is to the rotor is two rods about 16 millimeters in thickness and welded here, and then this particular part is attached to the gear system to rotate. That's all that there is to the rotor. There is zero engineering, 100% welding, vastly over-designed. It grinds the pounded yam to pulp in 30 seconds. Your neighbors will think you are drilling a borehole in your kitchen. It is made of stainless steel, and the pros are that it gets the job done. It gets it done fast. The cons are it is noisy, it got spoiled after 1 year, so it is unreliable. And when you try to fix it, you see that you have to replace the grinder inside, which is essentially getting a new machine. Now, I went back to the market again, and I got what was labeled yam pounder. By the time I got home, this Akai yam pounder was actually, the yam pounder here was actually pasted on it by the importer. Underneath this yellow sign, the original maker, if you look very deeply, this is a palimpsest, because below it, you see food processor was what the original maker wrote on it. It sounds Japanese. It's your brother and my brother that made it a yam pounder, and all the effort was in printing this yam pounder on it. They did nothing. Now, when you try it, you find that the rotor is vastly different from the rotor in the Nigerian-made yam pounder. This rotor is made of plastic, and you can see from the strength of materials that the highest stresses occur at attachment, and because of that, you can see the attachment is thicker than the tip. So you can see that whoever did this has added some engineering knowledge using static stress analysis into this. But the rotor here is sharp. The original culture where this thing was made was a place where they sliced most of their foods. They don't pound the way we pound in this part of the world. So the cutting edge of the rotor, you can see, is made for cutting. So now, in between these two, can we improvise? Can we do some stress analysis? And can we begin to see whether we can go from one end to the other and find a middle ground where we get a yam pounder that will actually do the job for us? Here is the coupling mechanism for the Akai yam pounder. It's lightweight and it's mostly plastic, can be 3D printed. So what the students did in course of time with this is to reprint all of this with 3D, redraw this in 3 dimensions, and print them out so that we have all these gear systems all made of plastic. And they worked surprisingly using the cheapest 3D printer elements. So after 3D printing this, we now decide to replicate the rotor coupling, find the basis for putting a static load to obtain an optimal shape that will beat the jam, or plantain or any other food you may want to pound. And then we try to optimize the results. So after we have done this, what we found is what we have on the left. So the rotor that came is on the right. The rotor that we discovered at the end of the day, we arrived at the end of the day, is on the left. Now, the modification of the Akai machine asks now the following: thicker blades with experience using the local welder version. So because of the local welder version that worked, we know that this blades must be thicker. Then we sweep it in the opposite direction. The static stress analysis suggests increasing the thickness of the rotor. And here we have the improved design. The problems we are still battling with is that the rotor sometimes disconnects. So the students are working on making a locking mechanism on this rotor. And by that time, we shall have improved an existing design by using two existing designs. I would have gotten a yam pounder that actually does some kind of averaging between the two. And we can now put this one out to static testing, to dynamic testing, and continue improving it so that we continue to get a much more optimal rotor and therefore a better grinding machine. Thank you.